So we start with turbulence from where we have left. Now, as I told you that there is a problem in solving the problem of turbulence, and the problem is that we have to go for very small number of cells, small size of cells. So let us see if we okay, let's forget about it. So the problem originates from the point that when we see that change in velocity, right, there are vortices and they are having okay, what we will do here, we will add a note here. That will be better. So let me specify the problem once again. The problem is if our size of the cell is like this, right, and the vertex size is like this, right. Now what will happen that we can only assign one velocity to it. This is one cell, right. So if we want to assign one velocity to it, this velocity is equal to 0, because you will average it out, you will find the velocity of this. Now what does that mean is, our solution is saying that the problem velocity of the cell, velocity of the fluid in the cell is 0, but it is having some velocity, alright. So this will create a problem. Now we have a solution to this, and the solution is that we divide it into 4 parts. If it is a 3D body, we can divide in 8 parts. Okay. Now what will happen if the vertex size is this? You can say the velocity here will be like this, here it will be like this, here it will be like this, and here it will be like this. Okay. So now you have 4 velocities. You have V1, V2, V3, V4. They together represent the cell, represent vortex. Okay. So instead of having one velocity, which is saying it is 0, now you have 4 velocity. So the solution available to you is you divide the cell in smaller parts. Now you can further divide it, right, and what will happen is that suppose you divide this now, cell, okay, let us make it here. We have cell like this, and this is the velocity, right, and we assume we approximated it with velocity this. Now if we divide it again, right, then we have 2 velocities or maybe 3 velocities, one here, and one here. We are approximating it. So the technique available to us is that we can keep on dividing the cells and we can get the exact velocity profile and the profile of other parameters. Now this technique fails because the size of these vertices is very, very small. So you have to go smaller than that, whatever the size of vertex, and then it goes so large then our computer fails. So this is the problem we are facing. Had it been so that our computers are strong enough, we could have made a very small size of the cell, and we could have overcome this problem. So now now this leads to a set of partial differential equations called Reynolds average Navier-Stokes equation. This is what the whole exercise will lead to, and they will be called Ryan's. Now, how do we find this? So one solution available is to take care of turbulence is to work with parameters averaged over time interval t star. Okay. Thus, we are going to rewrite the Navier-Stokes equations. Now, how do we find the average? That we have a parameter phi, and we integrate it over dt and divide it by the time interval. So we are integrating from t to t plus t star. Now t star is selected such that it is more than the, you can say, the frequency of the vortex. So that you come back to the same. So you are averaging, that means everything is taken care of that during that interval. Okay. So when you do that, what you are going to get, phi will become an average parameter. So there is a parameter phi prime or phi bar, which is average over t star. So now you can write that phi is equal to phi bar plus phi prime, and this can be shown like on the graph like this. What we are doing is like this. This is phi, this is time, and there are variation like this. Okay. So this variation is phi prime, and this value is phi bar. So basically you are dividing in two parts, the average and the oscillation. Okay. Now what will happen then, if you take the average of this phi average of phi will be phi bar, and the average of phi bar will be phi bar only, because that's a value throughout the interval, same value. And when you take average of phi prime, it will be equal to 0, because phi prime is a variation, right? So sum of that will be 0. Now if you take other parameters like velocity, you have u will be equal to u bar plus u prime, v will be equal to v bar plus v prime, w will be equal to w bar plus w prime, p will be equal to p bar plus p prime, and t will be equal to t bar plus t prime. So every parameter is divided in two parts. One is the average part, one is the fluctuating part. Now then we come to the theorems of averaging. Now this is, if you want to find out the derivative, this is the first theorem. This is regarding derivative. Okay. If you find the derivative, what you will get? You will get this this averaging function can go in, because your similarly your integral function, it will go in, because what is your x, let me actually I have ये जो है, जब हम डेरिवेटिव करेंगे तो डेरिवेटिव का जो ऑपरेशन है इसके अंदर एवरेजिंग अगर हम डेरिवेटिव की करेंगे तो बेसिकली इट इज़ सेम एज डूइंग द डेरिवेटिव ऑफ द वेरिएबल. सॉरी डूइंग द क्या कहते हैं डेरिवेटिव एवरेज ऑफ द वेरिएबल. सो ये जो एवरेजिंग हमारी है, जो आफ्टर डेरिवेटिव है, ये बिफोर डेरिवेटिव में इट इज़ वन एंड सेम थिंग. ठीक है. एंड क्या हो रहा है? इंटीग्रल में भी यही चीज़ होती है. इसको मिटाने का कोई तरीका नहीं है. तो इंटीग्रल में भी हमारा ये जो है क्या कहते हैं एवरेज है वो अंदर चला जाता है. फंक्शन का आप इंटीग्रल करने के बाद एवरेज करो या पहले करो, इट इज़ वन एंड सेम थिंग. और अब क्या, हाँ, फिर एडिशन में भी यही है. एडिशन में आप एवरेज बाद में करो एडिशन करने के बाद या पहले करो, एवरेजिंग में कोई फ़र्क नहीं पड़ेगा. ठीक है. और अब जो बेसिक प्रॉब्लम होती है दैट स्टार्ट्स फ्रॉम multiplication. Now if you are doing the multiplication, then the averaging after multiplication is not same as averaging before multiplication. The difference would be this. Okay, f prime ये आएगा. We will do this कि how we will get this, we will look at this. Now if you look at this, there is one thing to be noted here, that if you replace phi by phi bar, nothing will happen, because what is happening, your one parameter is replaced by another. So phi is replaced by phi bar as far as these three are concerned. So if you are doing derivative, if you are doing integral, or if you are doing addition, in all these three cases, on the left side there is a variable f, on the right side the f variable is f bar. So the things have changed from one variable to the second variable. So your equation will have either f or f bar. But when you look at the fourth one, the problem is on the left side you have two variables fg, on the right side you have four variables f bar, g bar and f prime and g prime. So whenever the multiplication is going to come, the problem is that you are going to get additional variables. Okay, and this is the basic problem in solving the turbulence using RANS. Okay, so this is we are doing why this problem occurs. So if you multiplied f and g, right, and after multiplication you are doing the prime average, so you can write it like this: f is equal to f bar plus f prime, g is equal to g bar plus g prime. You multiplied them and do the average. Now the multiplication, there will be four terms: this, this, this and this, right? Now averaging of a sum is same as averaging of parts. So this averaging after addition can be broken into averaging before addition. So you are doing averaging. So you are doing averaging of these four terms separately, right? Now then what will happen? Now these two terms and these two terms, they are equal to 0. Why? Because if you look at this, right, this term, what we are doing? You are doing average of f prime and g average. Now g average is constant, so you can take it out and you can do averaging of only f prime, but averaging of f prime is equal to 0, so this will become equal to 0. So what happens, these two terms go away, the other term is similar, in which one term is prime, the other term is average, right? But when you are doing this, multiplying this f prime with g prime, their product and their average may not be 0. A simple example I give you, if you multiply u prime with u prime and you find the average, this is not equal to 0. Because even if u prime is negative, u prime into u prime will be positive. So all these terms will always be positive. So their average cannot be 0. So same thing is there. If you are multiplying f prime by g prime, it's quite possible that f is positive, g is also positive. When f is negative, g is also negative. So thing is, what will happen, that you will not get, the average will be 0. So this term will remain there. Okay. Now this is the actual problem, because when you are multiplying, you are doing averaging after multiplication, and you want to convert it into after multiplication, you get this additional term. So what you are saying is, on seeing that on the left side you have 2 variables, on the right side you have 4 variables. Okay. So you have 2 additional. If you replace f by f bar, right? So your number of variables remains same. You can replace g by g bar, number of variables remain same, but you are going to get additional f prime and g prime. These are the 2 extra variables which are going to come. You have to look after them. What does it mean? The fluctuation of a parameter becomes important here. Okay. So now the problem. Prime quantities do not vanish during multiplication. As a result, on an averaging, we end up with additional variables. Thus, we would require additional equations to solve prime parameters. If there were no prime terms on the right side, there would be no extra prime variable. So this means the same thing as I told you. So these 2 variables which are coming here need extra equation. Now suppose you want to find the average of velocity. So this is the, if you want to find the average of v, it will be average of these 3 components and you will get this. Okay. Okay. Then if you want to find the average of product of u, you are going to get what? These 4 terms, we have already done that, and then these 2 terms will be 0 and this term will be not equal to 0. So what you will get is this. So if there is a product of velocity, you will get these terms as extra. Okay. Now in other words, you can say that if you are talking about v into u, now this is a multiplication of velocity vector with a one component of velocity, and you are going to get these components. Okay. If there were no prime terms on the right side, we could have replaced v with v prime. Now this is the thing. On the right side, your v prime is not vanishing. Had it been not there, we could have simply replaced v with v bar and our number of unknowns would have remained same. Okay. Now you look at this equation. This is continuity equation. Here we are not assuming fluctuation in rho. So you will find that this is equation is, there would be no change in here. Okay. If you are doing the averaging, your average, so what the components you have one is rho average and you have one velocity average. So it is made up of two variables. If you look at this equation, next one, momentum equation, now you see, look at this, right? Now if you are doing averaging of this, right, so I think we should put average here. Okay, anyway, so these are the terms here. Now these terms will be additional. ओके, बिकॉज आपने इसका जब एवरेज करेंगे, जब आप इसका एवरेज करेंगे ना, इसका ये एवरेज हो गया, ये हमने v, ये जो है v को भी हमने एवरेज ले लिया, यहाँ भी जो यहाँ पे इक्वेशन है, व्हाट वी हैव डन इज, ओरिजिनल इक्वेशन वुड बी लाइक डेल रो u बाय डेल t, ठीक है, प्लस डाइवर्जेंस ऑफ रो वी यू, ठीक है, और इसका एवरेज करेंगे आप ऐसे, ठीक, तो ये आ जाएगा इसमें डेल रो यू बाय डेल टी, प्लस इसमें जो आएगा एक तो ये कंपोनेंट आएगा रो वी यू, ठीक है, प्लस एक और कंपोनेंट आएगा डाइवर्जेंस ऑफ रो वी प्राइम यू प्राइम। वो कंपोनेंट मैं इधर ले आया हूँ राइट साइड पे ना। सो दिस इज द एडिशनल टर्म विच कम्स हियर, एंड द सेम थिंग इज फॉर y direction and the same thing is true for z direction. So what you are getting is your momentum equation has been modified. These terms are the extra terms which have come, and they are prime. They are not same as average. So all your original instantaneous one is gone. So instantaneous velocity has been replaced by what? Average velocity and prime velocity, right? So now, so these 9 terms, now these are the 9 terms which come here. There are 9 different variables are there, or at least you can say 3 variables are there. 3 different. Now the problem is how to solve them. These are mathematical equations. If you want to solve them, you have to have additional equations. Either you should be able to solve fluctuation independently, or if you are taking them in pair, then all these 9 equations should be there. Now these are random fluctuations, right? So you don't have any equation for them, and here you are stuck up. You have the variables, you don't have the equations. This is the problem we are facing. Okay. Now these are called Reynolds stresses. These 9 terms are called Reynolds stresses. Okay. And why do we call them Reynolds stresses? Because their units of these terms is same as that of stress. If you compare the unit, you will find that the unit of this is nothing but Newton per meter square, which is same as unit of shear stress or stress. They are called Reynolds stresses. There is nothing like Reynolds stresses. You don't know what it is. multiplying one fluctuation velocity with another fluctuation velocity, what does it mean? We don't know. We know velocity, we know average velocity, we know what is a fluctuating velocity, but what is it multiplying two velocity which are fluctuating? What is the physical significance of that? You are calling it Reynolds stress, but there is nothing like stress. And why you are calling it Reynolds stress? Just because their units are that of stress. Okay. So now the thing is, these equations contain 9 new terms, which are called Reynolds stresses. These terms are flow dependent and depend upon the nature of turbulent flow. On what will these depend? They are fluctuation in velocity. So basically they will depend upon what is the type of flow and what is the type of fluid. Right? Okay. Now, it is these 9 terms we must address to obtain the solution of the above equation. Now, unless until you solve them, you cannot find the solution. Right? So, and then we have no laws which govern prime variables. Now, how do we define these prime variables? Is there any law by which we can say fluctuation will be like this? It's a random fluctuation. Even when the fluctuation has started from a deterministic structure, that means from a point which is known to us, the first disturbance may be known. But the problem is, as it moves on, it diverges, it separates and mixes in the whole fluid. And the form it will take, we do not know. So, there are reasons for that, because we do not know how the molecular structure of the fluid is going to behave, because it's those molecular structure which are going to affect it. And then the molecular structure of the surfaces it is going to encounter. So, in a way we have less information, right? And we do not know what is happening. I can give you an example of Google Maps. How do they work? Now, you take a city map, Google Map. The Google Map tells you that which road, how much time it will take. How it is telling you? That tells you how many people are traveling, at what speed they are traveling. From there, it knows. Now, what the Google is collecting is the average number of people moving in that area. So, how much that road is crowded. Okay. But if you look at each man, he has a purpose, he has a direction. He knows where he wants to go. Right? Google is not bothered about it. So if you look at that particle, one person, if you sit at that particle, if you are in the mind of that person, he knows very well what way he is going, where he is going to take a turn, where he is going to stop, how much time, where he will return, all that thing he knows. Right? But what the Google is knowing is that how many people are going through this. And that is the information on which it is working. So, either you should be knowing how each particle is behaving, then you will be able to know address, and which becomes a humongous information. So much information, how will you get? And moreover, those particles are interacting with each other. So when two balls are colliding and they are big size, you can tell where they will go. It's very easy to predict. When the balls are of larger size, they come close, hit here, what angle they are going to hit, you can predict where they will go. But when their atoms are colliding, they are also like balls. You cannot predict, because you do not know at what angle they are going to hit. So for you it becomes a random information. And it's difficult to go to the molecular structure level. So because of the molecular behavior of the fluid, randomness is there, which you don't know. So in a way, you don't know that how that particle will be performing. So you don't know what is V prime, W prime or U prime. You don't know that. Right? So what in turn means that you have to find something, some way, because these variables have come. So now similarly, this is the equation for the energy, and here you get these terms: fluctuation in temperature and fluctuation in velocity. They do not cancel out, and there are three, because V has three components: U prime, V prime, W prime. So there are 3 here and 9 there. So total 12 unknowns are there. Okay. Now these equations contains 3 new terms. These terms depend upon the nature of the turbulent flow. If these 3 terms, it is these 3 terms we must address to obtain the solution of the above equation. So we should know what are these terms, not only these 3 and the previous 9. So we should know about these 12 terms. We have no laws for these variables, and therefore we must go for approximate equation. So we do not have the laws for this. If we have laws, we don't have the information. If the 2 balls are going to strike, we don't know at what angle they are going to strike. So in a way, we don't have any equation or any information about these fluctuation. Okay. Now the problem is that if you do not know, so your number of unknowns have increased by 12. You have to add as many equations to solve this. So what does it say? That RANS, Reynolds average Navier-Stokes equation, does not provide definite solution for turbulent flow. There are more variables present in the formulation than the number of equations available to us. Therefore, we need approximation model to solve such problems. Now we go for approximation. Right? So you understand that why this need has come. Now these models are, they are like Spalart, Almaraz, K epsilon, K omega SST, RNG, K epsilon. These are the few of them, and there are many more. On what does these models depend? These are approximate models, and they depend upon the nature of the flow, nature of the fluid, etc., etc. Right? So what people are saying, okay, if this is the type of flow, you take up this type of model. And we have found that we can get good solution from this. So you are making approximations and using them to find your solution. This is the state of affairs. All these models are approximate models. Therefore, validation becomes an essential part of the CFD solution simulation. These are approximate models. The theory behind them, there is some theory, but that is not full to the last, you can say, decimal. It is not to that point. there are approximations. So it's a big mix of, you can say, theory and empirical formulations. Like you find in heat transfer equations, there are many equations which people experiment. They propose that these will be, this will be the, this is how the behavior will be, and then they find the coefficients, etc., everything. So they are not basically, you can say, blind guesses. There is a lot of science involved in it. But then it is not till the end. At some point they make approximation. So all these models become approximation, which means that your solutions are not 100% true. These are, and that is why there are many models, and not only these, there are many more models. If it was a mathematical solution, there would have been only one model. So depending upon different types of cases, they have developed different models, and so there is a element of approximation here. Now, then what has happened is that this is RANDS. Beyond this is LES. This is also another model which is called large eddy simulation. Now, what does it do? This model actually solves for larger scales of turbulent structures, but approximates smaller turbulent structure. So what is happening is you have a bigger structure, you have a smaller structure. RANS is actually averaging this also and this average also. What LES does, this it takes care, but this is, it is average. So it is going a step finer. So the large eddy simulation, it is called large eddy simulation because large eddies are taken care of, but you are actually approximating the smaller one. Okay. And why this happens is because your computer programming becomes stronger, so you can reduce the size of the cells and you can break the larger eddies into, you can capture the larger eddies. If your cells are smaller, you can catch the larger eddies. Whatever the cell size of the cell is, you cannot capture the eddy less than that size. Okay, because within a cell, if a vortex is forming, you don't know anything about it, what is happening there. For you, it is a zero velocity. Then there is another formulation which is called direct numerical simulation. Now, the Navier-Stokes equations are solved for all scales of motions in turbulent flow. Now, this is going still deeper, and there are no approximations. So you become very small size cells are taken care of. Now, if you are doing that, then what will happen? Either your computer size should be big or your problem size should be small. So normally DNS is applied to smaller problems. So these formulations exist. People know programming is there. People know how to solve them, right? But when it comes to DNS, you cannot solve bigger problems, right? So as again the limitation is what? The size of computer, the capacity of the computer. As I told you before that CFD knowledge existed 150 years before. Why it cannot be used? Because the computer was not there. Same thing is here now. Now we are using CFD, we are using even DNS, but we cannot solve bigger problems because still we have not got the computers which we want. There is a hope that quantum computers will come and they are millions of times faster than the existing computer. Right? If they come in, they become a part of the, you can say, day-to-day life, then probably people will be able to solve this. Same thing here. With the increase in number of cells, computation time also increases considerably, and therefore at present these methods can be used only for computationally smaller problems. Okay. So this is the end of intro. We will stop here. So where we stand today, or you will find that our approximations, all our flows are turbulent. We are not able to escape turbulence. That is a natural phenomenon. Okay. And for solving the turbulent flows, we do not have any foolproof solution. Okay. So we have to go for approximate solution. Whatever turbulent model exists, they are approximate model. So when we are solving CFD problems, we are actually approximately solving the problem. And that is why when we were discussing right in the beginning, experimental part becomes very important. Because you are using approximate solutions, you must be validating and verifying those solutions experimentally, right? And that is why whenever you pick up CFD problem, there is always a issue of validation, right? So how do we actually go about solving a problem is in CFD, because if you are solving the old problem, there is no point. And when you come to a new problem, you are not sure that the model will apply here. So actually it is all guesswork. So what you do, you take a similar problem which people have solved, whose experimental solutions are available to you. You do CFD simulation for that problem. Compare the results with the experimental results. And if you are satisfied, then what you say that since my problem is similar, so the model which I am applying here, I can extend it to the newer problem also. So we move one step at a time. We solve a simpler problem using a CFD formulation, verify it experimentally or maybe analytically. Of course, analytical, we said that the moment the viscosity is there, analytical solutions are not possible. They are very difficult. They are not possible. Or I would say that we have not found it so far. So you take a problem which is a similar one, a smaller one, easier one, solve it experimentally, do the experiments, compare your results of the CFD simulation with the experimental results. Once you are satisfied, then you make a jump. That okay, this CFD problem can also be solved with this. Because I have done so far, it was good. the next step also it will be good. It's all approximation. Then that knowledge is added. Once you use that, you design system based on that, do experiment on that. That knowledge becomes a foundation for the next leap, next step. So this is how CFD works. So all the moment you are working with approximations. This is what the CFD. So validation becomes very important part of it, and that is why experimentation also becomes very important part of it. Okay. Maybe some date in future when all these approximations are not there, we will not require experimental work. Now you see where we made the approximations. This is the one approximation in the models you are making. Turbulent models, they are approximate. Now when you are going to convert these equations into algebraic equations, again there will be Taylor series and there will be truncation error, and you will be leaving certain terms. That would be the second stage where you are making approximations. Right? There will be third stage when you will be using shortcut methods to find the solution to those algebraic problems. Those algebraic problems also you will not be solving in a perfect manner. So approximation is bedrock of CFD. At each stage you are making approximation. Still we use it because it simplifies our problem a lot. And it is working. If it would not have been working, people will not use it. So this is how the CFD is. Okay.